Hi, this is Dr. Green, and we are doing some examples for the week 6 problems here. So in this first problem, we've got a researcher that wants to determine the mean trough dosage of a medication for a population. And we had a previous study that was conducted for the same medication, and the mean trough dose was found to be 320 milligrams. So that's a mean there of 320. And the standard deviation in that dosage was 25, and they want us to calculate the margin of error for a 99% confidence interval, assuming the previous study enrolled 200 individuals here. That's a sample size. So first of all, margin of error comes from the confidence interval formula. So let's go to the confidence interval table here. So that's table 622, and we have got one sample, and they were talking about mean, so this is going to be confidence interval for the mean. That's a continuous variable. So x bar is the point estimate, and then this portion right here, the z s over root n, that's your margin of error. It's the amount that you're adding and subtracting to your point estimate. So that's where this formula comes from. So E stands for the margin of error. E stands for error. So in there we need z, sigma, and n. So sigma was our standard deviation, 25. N, our sample size, 200. And that means we weren't using the 320, which was the mean. That's x bar. That doesn't get used. And then we need the z value to go with 99% confidence. That's in table 1b. So let's go to table 1b. So table 1b, we want 99% confidence. That value of z is 2.576. So now we just plug into the margin of error formula. So we got that 2.576 out in front times our standard deviation of 25. And we're dividing by the square root of that sample size of 200. And when I plug this into the calculator, I got 4.55. And that's going to be milligrams, because this was milligrams of dosage, trough dosage. So that's margin of error. In problem 2, we have a researcher who is conducting a study to determine the mean trough dosage of a medication for a population. We're going to assume previous study was conducted for the same medication, and the mean trough dose was found to be 320 milligrams. So that's a mean of 320 with a standard deviation of 25. Researcher wants to be 99% confident of the true mean trough dosage for the medication within 15 milligrams. So that's our margin of error. We want to know what sample size is needed. So this is going to be continuous data. Milligram dosage is continuous data, not dichotomous. We have one sample going on here. So this is continuous, one sample. Estimate. It is an estimate here because they said 99% confident. So we're looking at a confidence interval, and the sample size formula from table 8.1 is z sigma over margin of error quantity squared. So let me just look at that real quick. So this is continuous outcome, one sample here, right there. And we are looking at sample size for a confidence interval, and that is this formula here. So that's where I got it, table 8.1. So now we need the pieces here. So the standard deviation here, the total standard deviation was 25. E is your margin of error. We want to be within 15 milligrams, so that's telling us that's a margin of error. And then we are doing 99% confidence, so we need the z value to go with 99% confidence. That's table 1b. Let's go there. And so this is table 1b. Confidence level is 99% here, 2.576. So we do those substitutions. So z is 2.576. Standard deviation is 25. Our margin of error in the denominator is 15. That whole quantity gets squared. If you plug that into the calculator, you will get about 18.4. And we always round sample sizes up. So this will round up to 19 because you can't have 4/10 of an individual in your trial. So 19 individuals here are needed to get that 15 milligram tolerance margin of error there. Now notice that the 320 was not used here. So that's extraneous information. So a previous study told us that it was 320. Now if we wanted to actually compute the interval, then we would need the 320. That's our X bar. In example 3 here, we are using the same data again. We're conducting a study to determine trough dosage. The mean here was again 320. Standard deviation was 25. Again, we want 99% confidence, so our z-value is going to be the same. And within 15 milligrams. And we want to know what sample size is needed if the study is predicted to have, so what sample size again is needed if the study is predicted to have 88% retention rate. So what that means is that whatever sample you start with, only 88% of the people are going to keep with the study. 12% are going to drop out. So what we knew is that if we had 100% retention, that was the previous problem, then we needed 11 participants. Okay, but with 88% retention, we have to start with more than 11. So what that means is whatever we start with, only 88% of that starting number are going to stick with it. Well, let's let the sample size that we need, the larger sample size that we're going to have to start with, let's let that be cap n. And what we know is that our sample size of 11 here, little n, that's going to be 0.88, 88% of cap n. Well, if you just divide that 0.88 off both sides here, then we get that the cap n, the sample size we want, is just the old sample size divided by the 0.88. So you want to start with your 10.67, not the rounded answer. Divide that by 0.88. And you'll get 12.12. And we're going to round that up to 13. So if we get 88% retention, then we better start with 13. Okay, next problem here. Researcher wants to calculate prevalence here of iron deficiency anemia in a specific community among those that are 50 years of age and older. So researcher needs to know how many individuals who are 50 years and older need to be recruited. That's a sample size question for the study in order to ensure the prevalence will be within 2% of the true proportion. So that's your margin of error within 2%. Calculate the sample size if we desire 95% confidence. And then the national study showed that 8.2% of individuals age 50 and over had iron anemia deficiency. So this was the previous study. Okay, well, first of all, this is a dichotomous variable. Either you have anemia or you don't. And then this is one sample. Okay, so if we go to table 8.1, we are looking at a dichotomous outcome, one sample. So that's n p1 minus p z over e squared. So that's where I got this formula. So our margin of error, it's within 2%. So our e is 2% or 0.02. And then our p here, that's the accepted value, which is the 8.2%. We want to write that as a decimal, 0.082. And then the z-value that goes with 95% confidence, that's table 1b. So 95% confidence in table 1b is 1.96. So if we go ahead and compute our sample size here, this will be 0.082 is p times 1 minus p, 1 minus 0.082, and then times our z-value, 1.96. That gets divided by our margin of error, which is the 0.02, and then we're going to square that guy. So when I did that calculation, I got 722.95 to 2 decimal places. And we always round up, so we're going to round that guy up to 723. And I did want to mention that all of the formulas that we've been using here, we've been using formulas that are for confidence intervals and not formulas that are for hypothesis tests. So the formula that we used here, the P1 minus PZ over E squared, notice that that's sample size for a confidence interval. If they want these category, the sample size for a test of hypothesis, it will actually say in the problem that we're testing a hypothesis. Some of the clues here is that they're estimating prevalence within 2%, so that within 2%, you don't do estimating. It involves confidence intervals. So, and then that was true in some of the previous problems here too. They actually told us here we want to be 99% confident that we're within 15 milligrams, so we're doing estimating. Okay, it didn't say hypothesis test. So just wanted to make you aware of why I was picking things in the first column. So let's go ahead and take a look at the next question here. So in question number 5, we have a clinical trial that's being conducted in order to determine efficacy of a new drug that will be used to treat diabetes. We're going to measure efficacy with a blood test, hemoglobin A1C, and the researcher wants a margin of error for the level of H1AC to be less than or equal to 0.15. Okay, so that's our E is going to be 0.15, so I'll go ahead and put that down here. And then the standard deviation for those hemoglobin levels among diabetics were previously documented at 0.4, and again, that's standard deviation, so that's going to be sigma, so that's 0.4, 0.40. And then we want 95% confidence. That's going to determine our z-value for the confidence interval. Now here again, they also say assuming a 95% confidence interval will be used to quantify. They want to know how many patients should be recruited. So here again, they've told us a confidence interval. Now we do need to read a little bit carefully here because they're asking how many patients should be recruited for each group of individuals in the study, assuming a 95% confidence interval, to quantify the mean differences between the control group and the treatment group. So this is not one sample, this is 2 samples. We're picking 2 independent samples, a control group and a treatment group, but we want to know how many are in each group. So if we go over to table 8.1 here, so again 8.1 sample size formulas, then hemoglobin A1C are continuous values, so we want continuous and 2 independent samples, so that's this category here. We are using confidence intervals, so that's this formula. Okay, and that's the formula that I have here. And I could use n sub I instead of n sub 1 if I wanted to here. We've got 2 groups, n1 and n2 are the sample size of the 2 groups. So we need our z-value here from table 1b. That's going to go with 95% confidence. If I remember correctly, that was 1.96. So we'll go back to our table 1b. Yes, 1.96. I'd used that one before. So now we're all set to plug into this formula. So we've got that 2 out in front, and then our z-value is 1.96. Sigma was 0.4, and our margin of error is the E downstairs. That was 0.15, and then that whole thing gets squared. And then if you enter this into your calculator, you get approximately 54.6. And then remember, sample sizes, you always round up. So this will be approximately 55. So 55 individuals, and that's going to be in each group, because this is n sub I. That's not the total between two groups, that's each group. In problem number 6 here, a researcher wants to be sure that the mean difference, that's a key phrase here, mean difference in the change in heart rate has a margin of error of no more than 10 beats per minute, and the difference in the standard deviation between the mean heart rate from first medication used for tachycardia to the second medication is 22 beats per minute. We are computing the desired sample size required to ensure accuracy with 99% confidence, and it's a crossover trial. So mean difference there, that is your clue that we're looking at the mean of differences. So this is going to be a paired difference or matched sample experiment, and heart rates will be continuous here. This is not dichotomous. So table 8.1 will give the sample size formula z times the standard deviation of the differences over the margin of error, and that whole thing squared. So that is here. This is table 8.1. We have got continuous 2 matched samples here. We are using a confidence interval, so that is this formula here. So that's the formula that I'm using. The standard deviation of the differences. So this is, they described it as the difference in standard deviation, but that is 22 beats per minute. So this is 22. E is your margin of error, and we want a margin of error of no more than 10 beats per minute. So E is 10. And then we have 99% confidence, and so the z-score that goes with 99% confidence, that's in table 1b. So that's here, and we see 99% confidence, 2.576. And we'll go ahead and make the substitutions here. So 2.576. Standard deviation of the differences is 22. And then our margin of error was 10 beats per minute. And we are going to square that. And when I put that into the calculator, I got approximately 32.1. And remember, sample size, we always round up. So this is going to round up to 33. Now that's 33 pairs of measurements. So in this crossover trial, each subject's going to act as their own control. So we're going to have 33 pairs of measurements on each subject. So the subject will take the first medication, they'll make a measurement, and then they'll cross over and take the second measurement, and they'll have 2 measurements on each subject. So that actually decreases our sample size, whereas independent samples, we would need 33 subjects for the first medication and 33 for the second. Here we don't. We just need the 33 subjects.
In problem number 7, we are trying to estimate the impact that low birth weight might have on infant developmental delay. We're doing that by a retrospective case control study on new moms. We're given that the prevalence of low birth weight is approximately 5.3%. Question is, how many subjects should the researcher enroll in this study if the researcher wants 90% confidence? So There's a 90% confidence interval for the difference in proportions. And we want a margin of error of no more than 4%. So, and our prevalence was given at 5.3%. So first of all, this is a dichotomous outcome. So either your infants have low birth weight or they don't. Either they have the outcome or they do not have the, either they have that risk factor or they do not have the risk factor. And even developmental delay. Either they have it or they do not have it. So it's dichotomous outcome. So we go back to table 8.1, and we are looking at sample size for confidence intervals. We now have a dichotomous outcome, and we've got two independent samples. So that's going to be the low birth weight or no low birth weight. So basically your placebo and treatment, control and treatment. So that's this formula here. And I went ahead and brought that back. That's right here. And the n sub I means the number in each group. So we first need our margin of error, our z-value, and we need those proportions. So our margin of error they gave us as no more than 4%, so that would be 0.04. And then the proportion that they gave us, they told us here that prevalence of low birth weight was 5.3%. So 5.3%, which is a decimal, is 0.053. And that prevalence is going to be the same in both the control and the treatment group. And then the z-score that goes here with 90% confidence, that comes from table 1b. So again, table 1b is our z-values for confidence intervals, 90% confidence interval, 1.645. So z here is 1.645. And now we're ready to go ahead and plug in this formula. So P1 and P2 are both 0.053. Again, prevalence is the same for both the control group and the treatment group. So this is going to be 0.053 times 1 minus 0.053, and then plus P2 is the same, 0.053 times 1 minus 0.053, and now that gets multiplied by z over e squared. So our z-value is 1.645, and then our margin of error was 0.04, and that gets squared. So I plugged this into my calculator and I got just slightly over 155. It's 155.005, but we always round sample sizes up, so this one will go to 156. So that means that we should enroll 156 women whose infants had low birth weight, and 156 women whose infants did not have low birth weight. So that is, we are looking at 156 that had the risk factor and 156 where the risk factor was absent. In example number 8, we are looking at a study that's designed to assess association between exercise and then incident heart disease. Now, some studies had shown that people who exercise tend to eat diets that contain more fruits and vegetables, so better diet because they're more health conscious. So we're asking the question, could diet be a confounder in this analysis? So to analyze confounding for a study, we need to show two things. We would need to show that diet is associated with exercise. In other words, the two independent variables in the study are associated. And then we would need to show that diet, the possible confounder, is associated with heart disease. So they want us to use the appropriate hypothesis test for association between diet and exercise, the independent variables, at the 5% significance level, and then interpret our response. So the data that we're given is this. We've got a diet that's low in fruits and vegetables and a diet that's high in fruit and vegetables. And we divided the people up by the group that does not get exercise and the group that does. So notice here in the low fruit and vegetable groups, we've got 160 that have no heart disease versus 100 that have heart disease. But then when we look at the diet that's high in fruit and vegetables, we've got 60 with no heart disease and then 53 that do have heart disease. Now, once we look at exercise here, in the low diet group we had 96 with no heart disease and then only 42 that did have heart disease. So exercise definitely making a difference there. This 42 is less than half of the 96, so that's not as good as 100, or I'm sorry, not as high as 102 out of versus 160. And then when you look at the diet that's high in fruit and vegetables, the no heart disease was 50 versus 60, so it's approximately 1-to-1 ratio. But then when you added exercise in along with diet that's high in fruits and vegetables, we only had 43 that had heart disease and 244 that didn't. So this is a much smaller proportion out of the 287 total in the exercise group. So that makes us wonder if this is not a confounder. So first step, test if these guys are independent. So this is going to need a chi-square test of independence to determine if our two independent variables are associated. Notice here that diet and exercise status, those are the independent variables, and then heart disease is the dependent variable. So step one is to state our null and alternative hypothesis. So the null hypothesis is that exercise and diet are independent. Okay, so there's no difference, whether a person exercises and does have a diet, special diet, or not. And then the alternative hypothesis would just be the opposite. So exercise and diet then are not independent. So another way to say this is that the null hypothesis is that they're not associated, and the research hypothesis is that they are associated. The alpha value that we're given is 0.05. So next we determine our decision rule. So alpha is 0.05. Our degrees of freedom is defined to be rows minus 1 times columns minus 1. So we look at our table here. We've got, if we aggregate our data for diet and exercise, we've either got, for fruits and vegetables in the diet, we've got the low group and the high group, and then for exercise status, either no exercise or they do have exercise. Now, where did I get these numbers from? Well, low in fruit and vegetables, no exercise. So if we go back up to our original data here, so low in fruit and vegetables, no exercise, that was a total of 262. And that's this 262 here. And then I did that for each combination. So we've got two columns here and we've got two rows in our table. So R and C are both 2. So this is 2 minus 1 times 2 minus 1. That's 1 degree of freedom. And then we want to look the critical value up in the table for 1 degree of freedom, and alpha equals 0.05. So here we have the critical values for the chi-squared distribution. Our degrees of freedom are 1, and alpha here is 0.05. So our critical value is 3.84. So we go back here, we're going to reject the null hypothesis if chi-squared is greater than 3.84. So now we got to compute our test statistic, and remember the chi-squared test statistic. You sum up the observed value minus the expected value squared over the expected value. And then the expected frequencies, remember the way you get those is you do the row total times the column total divided by the grand total. So I've already done that in the table down here. So our row total is 400. Our column total is 375 for, I'm looking at this first entry, and then our gram total was 800. So that 187.5, that came from doing 400 times our column total of 375, and then divide by the 800. And then I did that for the other 4 boxes. So down here, the 187 is the same. It's 400 times 375, and then we're dividing by 800. For each of these 2 boxes, our row total is 400, our column total is 425, and then we're dividing by 800. So each one of these guys was 425, well, our row total 400, times column total of 425, and then divide by 800 our gram total. So that gives us observed and expected values. So now I'm going to go ahead and compute that chi-squared test statistic. So we're doing observed minus expected squared over expected. So for this first entry, observed is 262, expected is 187.5. So we're doing 262 minus 187.5. That difference gets squared, and then we divide by the expected, 187.5. We do that for the other cell. So for this cell, it's 113 minus 187.5. That's right here. Square it, divide by the 187.5. Up here, we're doing the difference between 138 and 212. Here, we squared it, divide by the 212.5. And then lastly, 287 minus 212.5 here, squared, divide by the 212.5. So when I computed this on my calculator, I actually got quite a large value, which is not unusual if there's a lot of difference here, if they truly are independent. So I got 111.44. And then we state our conclusion, step 4 here. So since our test statistic chi-squared, our test statistic value was 111.44. And what we do is compare that to the 3.84, which was our critical value right here. And since that 111.44 is greater than 3.84, it's more extreme than the critical value, we're going to go ahead and reject H0. So we're going to accept the null hypothesis, the alternative hypothesis as being true, which states that exercise status and amount of fruits and vegetables in the diet are not independent of one another. In other words, they are associated. So we've completed, in this problem, we completed the first step of showing confounding, and that was that diet is associated with exercise. Okay? And you should be doing something similar in your problem. And just a quick note, if our test statistic would have been less than 3.84, then we would fail to reject H0. We'd conclude that the variables were independent, that there was no association. In problem number 9, we're looking at the same study, and this is the same data from up above. We're trying to assess that association between exercise and incident heart disease, and we're asking, could diet be a confounder? So in order to do that, we need to show diet's associated with exercise. We've done that. That was shown in the previous problem, so that's done. But then, is diet associated with heart disease? So is this additional variable associated with the outcome? We showed it's associated with the original risk factor that we were looking at, which was exercise. So is it also associated with the outcome of heart disease? So they ask us to use the appropriate hypothesis test for association between diet and heart disease. That is going to be another chi-squared test. So this is going to be another chi-squared test of independence to try and determine confounding except that in this case we're testing for an association here between diet and heart disease. So our null hypothesis is going to be that diet and heart disease are independent. There's no association between this additional variable of diet and the outcome, heart disease, the dependent variable. And H1, the research hypothesis, is going to be that diet and heart disease are not independent. That is, there is an association. And that was the second thing that we needed to show in order to show confounding, that there was an association between the additional variable and the outcome, the dependent variable. So our second step is to establish our decision rule. So at alpha equals 0.05 again, we're given our degrees of freedom again are rows minus 1 times column minus 1. And if we organize our data in a table, we've got the diet status, low or high in fruits and vegetables, and then heart disease status. Either there's incident heart disease or there is no incident heart disease. So we've got 2 columns here, and we've got 2 rows. So this is going to again be 1 degree of freedom. And if we look that up in the chi-squared critical value table, that gives us that same 3.84. So now we're going to compute our test statistic from observed and expected values. So let me tell you how I set up the table down here. So I've got fruits and vegetables, I've got the low group and the high group, and then I'm looking at how many had incident heart disease and how many did not. So first of all, low fruits and vegetables in the diet, incident heart disease. I had a 144 there. So if we go up to the original data, we've got diet low in fruits and vegetables. Incident heart disease is in this column. The total is 144. That's this 144. And then I did the same for the other entries. I totaled the rows here, got row totals of 400, and I totaled my columns and got column totals of 240 and 560 respectively. So now I need to compute the expected frequencies. So those are the values that are in parentheses here. So how did I get those? Well, again, this 120 is row total times column total divided by grand total. So my row total was 400, my column total is 240, my grand total is 800. So this was 400 times 240, and we are dividing by 800, and that gives you 120. Same calculation here. And then I did the same over here. So the row total is 400, the column total is 560, so that 280 comes from doing the row total times the column total, 400 times 560, and then we divide by 800. And that's the same value here. So now we've got our observed and expected. So we need to sum up the observed minus expected squared over expected for each cell. So the first cell here, our observed was 144, our expected is that 120, so we want to do 144 minus 120. That difference gets squared, and then we divide by the expected, which is the 120. And then for this cell, it's 96 minus 120, so that's here, squared, divide by the expected. 256 minus 280 here gets squared, divide by the expected. And then 304 minus 280 here gets squared, divide by the expected of 280. When I put that in the calculator, I got 13.71 for my test statistic. And then since our test statistic, 13.71, is greater than our critical value of 3.84, we are going to reject H0. So that means we're going to accept the alternative hypothesis at the 5% level, which states that diet here, diet status, and heart disease, so the other variable and the dependent variable, are not independent. In other words, they're associated. Okay, if they're not independent of each other, then they're associated. So this establishes that diet is indeed a confounding variable, because, going back to the beginning of the problem, we had already shown that diet is associated with exercise. Now with this chi-squared test, we showed that diet was associated with heart disease, the dependent variable. Okay, and that's what establishes diet as a confounder.